Back another lecture, another boring lecture actually. I know a lot of people haven't been liking Discrete all that much. Me neither, to be honest. Not my favorite subject, not even the closest, just because too much English and I like math. So I'm gonna try my best to teach it to my best capabilities, even though I hate it. I hope you guys learned something, and if you don't, well, too bad, you just wasted your time. I will be going through the questions for homework questions for this lecture as well. So we're gonna start with propositional logic. Propositional logic, the best way you can think about it is somebody lying or not? That's really what it is. Is you'll read something like, is this a lie or is this true? And if it's a possibility that's either a lie or a true, then it's a proposition. But if you cannot determine whether it's true or false, then it's not a proposition. So we're gonna go straight ahead with the first example. I feel like white is a bad idea. We'll go with red today. Toronto is the capital of Canada. So you see, when you read this, is this a proposition? Is this person who's saying this, are they lying? Are they telling the truth? Or is their statement even has a true or false? So you see, when I say Toronto is the capital of Canada, Toronto can be a capital of Canada, or it cannot be a capital of Canada. I could be either lying or I'm not lying. Therefore, it makes it a proposition. Now, what is the value of this proposition? Is obviously false because it is not the capital of Canada. 1 plus 1 equals 2. Now, you can think this is math and this will always be true. Yes, but this is still a proposition because I can lie. I can say 1 plus 1 equals 3. That would be me lying. But I'm saying 1 plus 1 equals 2, which is me not lying. Therefore, this is true and it is a proposition. 3 is greater than 5. This is also a proposition because, again, I can lie. So you see here, I am lying. 3 is greater than 5, which is not. Therefore, this is false, and it is a proposition. What time is it? You see this one, this is what I call a proposition. It's not truth or a lie when I tell you what time is it. Now, you can answer me with a lie, or you can answer me with the truth. Your answer will be a proposition. However, this part itself is just a question. I'm not proposing something to you and telling you is this true or false. I'm asking you something. Therefore, this is not even a proposition. Now, this you can think is similar to this. However, this is not a proposition. The reason for that is because I am still asking you, what is x? Now, I'm not technically saying find x, but you don't know what x is. So you can't even say this is true, and you can't say this is false. Because if x was 1, this would be true, and if x was 2, this would be false. So you really can't say whether this is true or false, therefore this is not even a proposition. Now, when it comes to propositions, we have a couple logical connectives. What do these do? These just let us combine statements you can think of. So the first one is negation. This one is just if something is true, you turn it false, and if it's false, you turn it true. That's basically what negation is that if I say a potato, right? Oh, I didn't spell that right. Potato. Dude, English is not Englishing, I'm telling you. So if I negate this, this will just become I am not a potato, right? It's whatever the statement is, it has to be a proposition. So see, if I said what time it is, and you negate that, what does that do you? What is not time? It is like, it doesn't make sense. So you can only negate something that's true or false, and then when you negate it, it turns to the opposite. So if it's true, it turns false. If it's false, it turns true. Conjunction, you're basically combining two things. So I'm saying like true and true. By the way, when you're using any of these, think about it as a whole. So don't think about it like, true and true. Like the way you answer this, it would be what is the whole thing. So you see, I'm combining. I'm saying true and true. That gives me what? True, because I'm saying true and true. It's like true plus true, like 1 plus 2 is 3. So true plus true is true. If I'm saying true plus false, well, that's false. Because, for example, if I say I am, let's see, I'm trying to think of a good sentence. But actually, I think we're going to go through examples down below, and I feel like that would help you better than just me making an example on the spot. But I hope you do get it. If you don't, just wait, and then we'll go through more examples. Or is this similar to and, except the opposite? So I'm saying this or that. So when I'm saying like A B, if A was true, then this whole thing would return true, because I'm saying it's either this or this. I just need one of them to be true. So if A is true and B is false, that's still true because I only need one. If they're both false, then that's false because I said I only need one and I didn't get nothing. Now, if they're both true, that's still true because, like I said, I only need one. So that's the OR. The XOR is more exclusive, which it says, exclusive OR. This one is like specifically said, I only need one. Like I literally only need one. Anything more than one is false. I don't want that. So if they're both false, obviously that's false because I said that I only need one. But if they're both true, that's also false because I said I only need one. And so if only one of them, so if it's true, false, that would return true. So if this was true and this was false, remember I want just one of them. So therefore this would return true because I have one true. But if they were true and true, and this is an exclusive OR, that would return false because exclusive OR, I say I exclusively only want one thing. Conditional, you can think as a conditional like an if then, like if I go swimming, then I will get wet. So that's really what conditional is. Conditional, you can think about it is someone lying. That is probably the easiest way you can go about it. We'll do a quick truth table because it is a little bit confusing, but it's not too shabby. So P, we have Q, then we have true, true, false, false, and then we have true, false, false. So see we have all different combinations, and now we'll do P implies. So this arrow means implies, as you can see right here, implies Q. So if P, then Q. All right, so what I'm saying is if P is true, then Q has to be true. Okay, so here, if P is true, then Q has to be true. Like if I say, if I go swimming, I will get wet. So if I do go swimming, then I have to get wet. Therefore, I didn't lie. I said the truth. And then here, this is where the problem is. If I say, if I go swimming, then I will get wet. But what I'm saying here with the true or false, I'm saying, if I go swimming, since this is false, it says, if I go swimming, then I will not get wet. That doesn't make sense. I just lied. Therefore, this is false. So that's how you can think about it in terms of the if conditional, the implying, is this person lying? So here, I say, if I go swimming, if I don't go, so because since this is false, if I don't go swimming, then I will get wet. Now you see, I didn't lie here. Now I did say if I go swimming, then I will get wet. But as you know, getting wet is not the only way, like swimming is not the only way you get wet. It could rain. So here, I didn't really lie. I did get wet, but I said only if I go swimming. Sorry, I didn't say only if, so this is what this is for. I didn't say only if I go swimming, I'll get wet. I said if I go swimming, I will get wet. I know it's a little bit weird, it's too much English, I hate it, but get used to it, do practice, you'll be fine. So I hope the point gets across is that you just want to see if I'm lying. Here, I didn't go swimming, but I still got wet. That's possible. I didn't lie, therefore it's true. And same thing here, I didn't go swimming and I didn't get wet, which is I didn't lie. Because I said if I go swimming, I get wet. So if I didn't go swimming, I don't get wet. Therefore it's true. Another way you can think about it is whenever you're the one implying, so this one implies on Q, right? So if P is true, if P is false, then it will always return true regardless of what Q is. Because Q doesn't depend on P. P just says, hey, if I'm true, then Q can be true. And if Q is true, then I didn't lie. And if Q is false, then I did lie. But if I'm false, then regardless what Q is, I didn't lie because Q doesn't depend on me. You get what I mean? I hope you do. I'm saying you get what I mean as if you can just answer me. But that's that. Biconditional, actually, I'm probably going to put that back in. I'll get rid of all the little gibberish things. Biconditional. Oops. Okay, so, and this is biconditional. Biconditional basically states if and only if. Like this is true if and only if this is true. So what I'm saying here is P is true if and only if Q is true. Is Q true? Yes. Therefore this is true because I didn't lie. Same thing here. So I'm saying P is true if and only if Q is true. But P is true even though Q is false. So therefore, this is false. I lied, right? Same thing here. I'm saying P is true if and only if Q is true. Now, Q is true, but P is not true. So again, I lied. And then the last one, again, I'm saying P is true if and only if Q is true. And then since Q is false, P is also false. So I didn't lie. Therefore, this is true. So this is basically what we're doing. We're trying to find who's the fucking liar. It's annoying as shit, but whatever. Welcome to discrete mathematics, or more like I like to call it, discrete English. Let P denote I just won the lottery, and Q denote I am buying everyone a pony. So we're gonna do this actually in text because I feel like that would be easier to type out. Hello, can I? Okay. Well, actually, we'll just type here. Okay. So negation of not P. So as you can see, right here, I just won the lottery. Not P. If you remember up here, we said when you not something, you make it the opposite of what it is. So if you just won the lottery and you want to negate it, then you just say I did not. Oops. I did not win the lottery. Okay? So it's pretty simple at this level of sense, but it does get a little bit spicier, but nothing you can do. P and Q. So what I'm saying here is basically I just won the lottery and I am buying everyone a pony. That's literally what it is. So you'd say this sentence and you say and this sentence. Do practice. So you just remember what these symbols mean. They are up here. So you see this is an and. You just practice a couple times to be honest, and you kind of just get used to it. So I know it looks gibberish at first, but it's not too bad. Inclusive or. So disjunction, or in other words, inclusive or. P or Q. So I'm saying basically I just won the lottery or I am buying everyone a pony. So if either one is true, the whole thing returns true. So if I won the lottery, of course I didn't lie because I said I only want one to be true. If I do win the lottery and I do buy everyone a pony, again, didn't lie. This should return true. And if I don't win the lottery and I still buy everyone a pony, still I didn't lie because I just said I will either win or I will buy everyone a pony. If I do one or if I do both, that's great. Exclusive or basically said I either win or I buy everyone a pony. I cannot do both. That's what the exclusive or does. So you could say I just won the lottery. If I'm trying to think, are these tables the same actually? Never really thought about that. No, they're actually opposites of each other. So you see, with an exclusive or, these are actually true and these are false. They're inverse of each other, you could say. So for this one, what I'm basically saying is I will only be true if I only do one of them. If I do buy everyone a lottery and I buy everyone a pony, then that would be false. Okay? So that's that. Recall, P denotes I just want lottery. So this is recalling. This is the conditional. This says if I win the lottery, then I buy everyone a pony. Remember, this is a implying if then. So you see, if I don't win the lottery and I do buy everyone a pony, I still didn't lie. I said if I do, I'll buy everyone a pony. But I never said if I don't, I won't buy everyone a pony. I just said if I do, I will buy everyone a pony. But if I do and I don't, if I do win the lottery and I don't buy everyone a pony, then I definitely lied. Because I literally said if I win, I will buy everyone. But if I don't win and I still buy everyone, I didn't lie because I never said if I don't win, I don't buy everyone a pony. So I hope that gets it across. Converse, contraposition, and inverse. It's really simple. With converse, you can just, you see it's PQ, you just flip them. This will go here and this will go there. Contraposition is you flip and negate. So you see we negated them as we flip them. And also inverse is you don't flip, you just negate. Do you need to know these? I would say possibly. Do you need to memorize them? No. As you practice, you will kind of get it. Biconditional basically says I will win the lot if I win the lottery. Oh wait, no, how do I word it? I will buy everyone a pony if and only if I win the lottery. That's what it says. So what it says here is I am buying everyone a pony if and only if I win the lottery. So if I don't win the lottery and I do anything, then that would be false. Okay, so that comes us back to this table. Okay, so by conditional, here write the following as logical formulas, and if applicable, state the corresponding converse and contraposition. If Bob goes to the party but John does not, then Mary goes to the party too. So we can break this down into a couple, couple variables. So we'll say so Bob goes to the party, we can make that as one variable. John does not go to the party, that is another variable. And then we say Mary goes to the party. This would be another variable, right? So now we have all three variables. If you want to put it into a formula, what we're saying is if P, okay, so we're going to say if P, so remember, when you do a logical formula, this is the if implies, right? So like it's not if P. But actually, I'll do it like that and then I'll convert it. So what we're saying is if P, he says but, so I'm saying if Bob goes to the party but John does not, then Mary. So let's say Bob goes to the party, John does not, Mary goes. Bob goes to the party, John does go to the party, then Mary does not go to the party. Like if I tell you this as a person, like, hey bro, if Bob comes to the party and John doesn't, then I'll come. But if John does, then I won't come. Right? That's basically what I'm saying. Because I fucking hate John's guts. Sorry, John. But if Bob goes to the party, but John does not. So what we're saying is and, right? If Bob goes to the party and John does not, then I'll come. But if Bob goes to the party and John also goes to the party, then I'm not going to come because I don't want to see John. But also, if Bob doesn't go to the party, then I won't come because one of them is Bob goes to the party and John does not. So I need both of them to be true or else I'm not going to go. Okay, so I'm saying if P and Q, then R, right? And so if I put this into logical, I'll say P, so in brackets, P and Q, then R. Whenever it is raining, it is windy and it is not sunny. So whenever it is raining, I'm saying if it is raining, basically, if it is raining, then it is windy and it is not sunny. I mean, this one is very self-explanatory. So you can just say, well, it is raining if it is raining. Well, you don't need if, that's a logical, what was it? Get used to the wording, logical connective. So we don't need it as a variable. So it is raining is one. It is windy, that's another. And it is not sunny, that is R. Now, how do you know? Like, you're seeing me here putting these letters on all these statements, and you're like, how do I know? Where do I put the letter? Like, these are words. Like, can I just put the letter here? Like, how do I decide where to put the letter? The way you decide where to put the letter is you'll read one part of the sentence, and you're like, is this a proposition on its own? Right? So if I say it is raining, is that a proposition? Remember, if we go all the way up here to this part, we said something is a proposition if it has a true or false value. If it doesn't, then it's not a proposition. So now when I go back down here, it is raining. That can be true or false. You can say no, it's not raining, and you can say yes, it's raining. Therefore, that's a proposition. It is windy. Again, true or false. It is not sunny. True or false. So that's how I know where to put my letters or my variables. So now what am I saying? Whenever it is raining. So I'm basically saying if it is raining. So if P, then, or let's try the actual word, then it is windy and it is not sunny. So we said this is R, but what you always want to do is set your variable to the non-negated sentence. So this is supposed to be not R, because R, it is sunny. It is sunny. Oh, I can't fucking write. It is sunny would be R. Therefore, this is it is not sunny. So this is negating R. Okay? So always make sure you have it in you have like the, how do you say it, the true value of the statement as the variable, and if it's telling you the false value, then you negate that variable. Okay, so if P, then Q, well, I can just say then Q and R, well, negated R. And so if I'm putting this in logic, I would say P implies that Q and R must be true. Okay? Consider the following logical formulas. If P, then not Q and R is same as, are we supposed to like write in what terms? If P, what is he trying to say, is same as, well, like I could say like same as what? P implies R and not Q. The problem with his PDFs is he doesn't have an answer unless you have an Adobe and you can fucking click the next and shit. So I'm not sure what he meant by this part of the lecture. If P, not Q, and R and this are not the same. Okay, so here he's saying basically prove is this the same or not. There are two ways you can prove it. You can either simplify both and see if they match. The other way is you can do a truth table. We will be going through truth tables in a bit, so I'll skip this part. And the simplification will be in later lectures, so we'll also go through that part. A bit string is a finite sequence of zeros and ones. Each 0 or 1 is called a bit from binary digits. Interpreting 1 is true and 0 is false. That's all you need to know, really. That's the most important part. These two. Forget everything else. That's basically what we're saying is binary 1 is true and 0 is false. Now he wants to apply it to this. So all you got to do, honestly, is just 1, 0, 1, 1, 0. So that's this part. Right under it, you do 1, which is the y variable, 0, 1. And now you can do the and or. So true and true, remember, 1 is true, 0 is false. 1 and 1, true and true, is, so we're doing right now the and. 1 and 1 is 1. Remember, true and true is true. Oops. Is true. So that's what they're basically trying to say. False and true is false. Because remember, the and says they both have to be true. They have to be both true. If they're not, then it will always be false. Therefore, this is, I don't know why I wrote that. That would be, whoa, come on, man. Okay. So that would be 0. This would be 1. Remember, true and true. True and false is false. False and true is false. Now the or, now right under it, I'm going to do the or. I'll do it in a different color. So actually here I'll do this as the and I'll do this as the or. So the or states either one have to be true or they both. Like, I don't care. Just at least give me one. Please, bro. At least give me $1. Okay? So what this says basically, okay, so 1 or 1, that is true because I at least have 1. Again here, this is 0 or 1, which is false or true. I said at least give me 1, so I have 1. This is 1. Again, true or true, true. True or false. Again, I only want 1. So, okay, so I hope that was simple enough. And then we'll do in blue, we'll do the XOR. Remember, XOR isn't exclusive. What I'm trying to say is I only want 1. Don't give me more than 1. Don't give me less than 1. I only want 1. So, and I don't mean 1 as in the letter, but I mean 1 as in one true value. And so now if we're doing it, 1 and 1, remember I said I only specifically want 1. I have 2 trues, so that would be 0. Here, this follows what I said, which is I only want 1. Therefore, this is 1. Again, there's 2 of them that are true, which I don't want. 0, 1, and 1. Okay? Truth tables of compound propositions. So this kind of gives you the rules. You don't really need to memorize any of this. I'll tell you the juice right now. Actually, I do like a little more. The juice basically says how many rows do you have? So a truth table, if you think about it, a truth table looks like this, right? And you'll have your variables up here. So they're basically saying how many rows. So this is a row, okay? Just in case you don't know, this is a column and that's a row. If you want to remember, a column is like climbing a ladder, you're going upwards, and a row, you're just like don't remember row, just remember a column, and then whatever opposite is the row. Okay, so when it comes to a row, so which is what they're talking about here, if proposition consists of n variables, table should have 2 of n. So let's say I have P and Q. How many rows should I have to get all possible solutions? Like, true, true, false, false, and then you have true, false, true, false. So this is all the combinations you can have with only 2 variables. And so what they're saying is, if you want to know how many rows you should have, you want to take the number of variables. These would equal n. So I have 2, right? And then all you got to do is 2 to whatever n is, to the 2. And that would give you 4. And as you can see, we have 4 rows. And so if this was another one, right, then I could do, okay, so true, false, false, true. These are all different combinations, but you can see I could have more. For example, I could have false, 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 right? So how do I know how many rows I have, or I should have? What you'll do is just, again, 3 variables. This n would be 3, and so 2 to the 3, which is 8. So I gotta have 8 rows, and that would cover all your different scenarios. So that's this one. Table should start with 1 column for each variable, list variables. So like this is obviously a no-brainer. I don't think you need to memorize this. Each column has just 1 variable. Like you're not gonna have P and R and then have true and true. Have ith variable column filled by alternating. This is basically, they're basically telling you how to fill the table. Listen, all you need to do is just make sure you have every combination. If you want to follow it like this, I like to go with the 1-1-1. So I'll show you guys this method in case you do like it more. And if you don't like it, then you can go ahead and read that and then follow that and memorize it. But this one I found the easiest one. I learned this from computer architecture. So credit to Mr. Eric Rappos. Well, actually not Eric Rappos because I didn't go to lecture. But I don't know how I learned this, but it made sense. Anyways, so we're gonna do the P, Q, R, just because the more kind of clarifies how to do it. P, Q, and R. And we're gonna have, again, we clarified earlier, I don't need this section, so we need 8. So 1, 2, 3, 4, 5, 6, 7, and this is the 8. So the way you want to do it is first start with 0, 0, 0, and this would be false, false, false. Okay? Then what you'll do is you'll increment from the right all the way to the right. This is when you start incrementing. So then you'll do 0, 0, 1. Then 0. What you do is whenever there's a 1 and you add 1 to it, so right, remember how I said you increment from the right? So 1 plus 1 in binary, remember binary is only 0 and 1. So 1 plus 1 is actually 0, and you increment the one to the left of it. Okay? So what will happen is if I add 1 to this row, this will turn to 0 because I incremented it. This one will turn 1. And then again, so you'll go, okay, 0, 1, increment to the right. The 0 you can increment to 1. Okay? Again, you want to go again. Okay, I got to increment to the right. You increment this, becomes 0. This carries. You increment this, becomes 0. Carries. You increment this, becomes 1. You do it again. 1, 0. Increment the right one, which is fine. 1, 1. You increment this one, this will turn 0. You increment this one, this will turn 1. And then again, you have 1, 1. You increment this, 1. Now you have all combinations. So what will happen is now you'll have, false, 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 true, false, true, false, and so on, right? And so that is the easiest way I found to do it. Now, obviously when you do 2, you don't really need to do this. It's just true, true, false, false, and then true, false, true, false. However, when you have 3 or 4 or 5, it's very hectic for you to kind of try to figure out like all the combinations. This, I found the easiest way. You just keep carrying, you add to the rightmost and you carry. Add to the rightmost and you carry. Okay, so build the truth table for this. Let's do that. I'm gonna remove this. If you want it, take a picture. Or actually, let's return that. I can just fit it in here. So a truth table for this. What you want to do is the first thing is just have the variables P and not Q. If you have any other variables, put them in. So we're gonna have P and Q. Since there's only 2, we only actually need 4. Actually, I'll leave those for later because we do have more things to fill in. Okay, now you want to break them down to smaller problems. So we have this as one problem, or actually even smaller. This as one problem, so you'll have, I don't know why I put that there. Whoops. So this will be Q, this will be not Q. So that's one problem. Then you can group this whole thing together, which will have P or not Q, right? And then we can group this together. You basically just want to go as, just break it down to small pieces, and then you want to do the whole thing now, which is P or not Q, then P and Q. So what you want to do is, like we said, for 4, my straight lines are so straight. As soon as I said that, crazy. Whoops. I know this is in the way. Sorry guys, but deal with it. Too bad, too sad. Okay, so we have true, true, false, false, and then we said true, false, true, false. Okay, now with this one, you gotta negate Q. So whatever Q is, it's to the opposite. So it would be false now, true, false, true. This one is an or. So what I'm saying is P or not Q. So I'm saying P or not Q, which is, I want this column and this column. Now this is an or, therefore what I say is I want at least 1. You give me 2, that's nice, but I at least want 1 to be true. So true or false, we at least have 1. So that's true. True and true, we at least have 1. True, we have none. That's false. And then we have at least 1. This is true. Now you go to the next one. This is an and. And says 2 must be true. 2 of them, they have to be true. You can't have one or the other. You can't have both false. You at least need both to be true. And so P and Q, we're looking at now these columns right here. And so true and true is true. True or false, this would be false. False and true is false. False and false is false. Now you want to do the whole thing. But since we broke this down to a small problem, you actually can look at this whole problem as this column, if and only if this column. Sorry, not if and only if then. So if this column, then this column. And remember, we said if this column, then this column is true only when you're not lying. So let's see when I'm lying and when I'm not lying. So I feel like, did I do this wrong? P or not Q, false. Okay, so this is right. And then P, okay, no, this is fine. Did I write it wrong? No, it looks fine. Okay, so what I am saying here, I'm saying this, if this, then this. So I'm saying if P, whatever this statement is, if P is true, then Q has to be true, which I didn't lie, because Q is true. So therefore this is true. Now if I'm saying if P is true, then Q has to be true, or well, this, whatever this statement is, like what I'm basically saying P and Q is I'm assuming this whole thing now is P, and this whole thing now is Q. So to not confuse you guys, let's assume this whole thing is S, and let's assume this whole thing is T. So this whole column, I'm trying to make space, but it's so fucking crowded. What color is not visible? Okay, we'll do this one. So assume this whole column right here is S, and assume this whole column is T. Sorry for the messy notes. It's just typed on space right now. Okay, so I'm saying if S is true, then T has to be true, which it is. Therefore, it's true. Now here, if S is true, which is S is true, then T has to be true, but T is false, so I lied. Okay? Here, what I'm saying, if S is true, which, well, S is false, then T is true, and T is false. So I didn't lie. I said if S is false, then T is false. Just like saying if S is true, then T is true. There's no lie in that. So this is true. And here, again, this is the same as this one. So that would be false. Okay? Now we're going to do a couple homework questions. I'm going to run through them real quickly because I don't want to waste your time. Which of these sentences are propositions? What are the truth values of those that are propositions? So, again, how do you know it's a proposition? It has a true or false value. The second part basically says, is it true or is it false? So, is this a proposition? Boston is the capital of Massachusetts. This can be true or false. Therefore, it is a proposition. So this is a yes, it is a proposition. And is it true or false? I believe Boston is the capital of Massachusetts. Miami is the capital of Florida. That can be true or false, therefore it is a statement. And this is false because I believe what was the name of the fucking, I can't remember the name of the city, but it's definitely not Miami. 2 plus 3 equals 5. This can be a true or false because I could have made this 6 and made it false. So this is true, therefore it is a statement. Again, this is true, therefore, wait, is this true? Lol. No, this is false. I want to see the number. This is false, yet it is still a proposition. Dude, my English is like, as you can tell, fuck. What is going on? Okay. X plus 2 equals 11. This is not true or false because you don't know what X is. You cannot guarantee this is true or false. Therefore, this is not a proposition. Answer this question, again, you can't say this is true or false. You can say, no, I'm not going to fucking answer this shit. But it's not true or false. Therefore, not a proposition. What is the negation of each of these propositions? Whatever the sentence is, you just basically want to go the opposite way. So if I'm saying Linda is younger than Sanjay, then all you say is Linda is not younger than Sanjay. May makes more money than Isabel. You can say May does not make more money than Isabel. Mosh is taller than Monica. Again, Mosh is not taller than Monica. Abby is richer than Ricardo. Abby is not richer than Ricardo. You get the flow of that one. Let P and Q be the propositions. So this one, I will have to type it because it's a lot of typing. Okay, so actually, first let me write it out. So, oh wait, actually no, I can still type that. So P equals swimming at the New Jersey shore is allowed, and Q, equals sharks have been spotted near the shore. Okay, so the number A, what we're saying here is basically not Q. So sharks have been spotted near the shore. Sharks have not been spotted, right? Near the shore. For B, I'm saying P and Q. So swimming at the New Jersey shore is allowed, and sharks have been spotted near the shore. So I'm allowing them to swim, and there's sharks, so nice, they're gonna die. C, I'm basically saying swimming at the New Jersey shore is not allowed, or sharks have been spotted near the shore. So again, swimming at the New Jersey shore, is not allowed, or sharks have been spotted near the shore. Okay, now I'm gonna go a little bit to the harder ones for G and H. Okay, just because that just annoys me. Just because I feel like you guys get the flow. Hello, what's going on? So I just want to do the harder one so you guys kind of get it. P, if and only if, not Q. So just P, which is swimming at the New Jersey shore is allowed, if and only if sharks have not been spotted near the shore, right? So this is P, if and only if, not Q. And then we have H. What I'm saying here is not P, so swimming at the New Jersey shore is not allowed. And what I'm saying is now P or not Q. So, and swimming at the New Jersey shore is allowed, or sharks have not been spotted near the shore. Okay, so I know it doesn't make sense in plain English, but that is how you do it. You just want to read it word for word. This one does get a little bit trickier, so do hang on for this one. It is, I would say, more important than the last one. So here they already write it for you, which is nice. Write the proposition using P and Q logical connectives, including negations. So now we are actually doing the opposite, which is taking a sentence and turning it. So you do not drive over 65 miles per hour Here says you drive, so we are negating P. So for A, what you're doing is just negating P. For B, you drive over 65 miles per hour, but you do not get a speeding ticket. So you drive over 65 miles an hour. That is P. We didn't change anything. But you do not get a speeding ticket. So you see here I'm saying basically and. So if I tell you, you drove past 65 you drove past 65 miles per hour, but you didn't get a ticket, is the same thing if I said you drove over 65 miles per hour and you didn't get a ticket. It's the same thing. So this is and, not Q. For C, you will get a speeding ticket if you drive over 60 miles an hour. So this would be the same thing if I said if you drive over 65, then you will get, right? So P, then Q. If you do not drive over, so this one kind of just has in the if then. So if you do not, which is if not P, so this is for D. Whoops, that's a horrible looking D. So this is not Q, not P, then Q. Oh, it says then you will not. So if you do not drive, then you don't. So not Q. Okay. E, driving over 65 miles per hour is sufficient for getting a speeding ticket. So basically this is like an if statement. If I say that, or if I say if you drive over 65, then you get a speeding ticket, is the same thing. Okay, so I'm basically saying P implies Q. You get a speeding ticket, but you do not drive over 60 miles an hour. So this, again, the but is like an and. So if I said, hey bro, you got a speeding ticket, but you didn't go over 65, and if I said, you got a speeding ticket and you didn't go over 65, is the same thing. Now, I don't know English, but I definitely know these are the same thing. So what I'm saying is basically, but this is like flipped, so you could say Q. Bless me. Okay. But you do not drive over 65 miles an hour, so I'm saying and, not P. It's the same thing, so this equals this. They're exactly the same thing. They're just flipped. Wait, nope, this is, Q is negated. Sorry, I lied. I guess, well, that's not equal, but this is the same thing as if I said not P and Q. I just flipped it, but nothing really changed, as in the logic. Okay, so that's F. G, whenever you get a speeding ticket, you are driving over 65 miles an hour. So what I'm saying is, I'm basically saying, like, for sure, right? I'm saying whenever you get a speeding ticket, you have to be driving over 65. Like, I'm basically telling you, you are, right? It says here, you are driving over. So this is like an if and only if. So I could say G, I'm saying whenever you, or is that an if? I feel like that kind of goes both ways. Whenever you get a speeding ticket, you are driving. Would I be saying if you get a speeding ticket, then you are driving over 65? Because that also makes sense, right? That does make sense if I say if you get a speeding ticket, then you are driving, right? So I feel like that would go. Because I'm not saying you get a speeding ticket only if you're driving over 65. I'm just saying if you got a speeding ticket, then you're driving. But if you're driving over 65, it doesn't mean you got a speeding ticket, right? So I feel like this is an if then. So this would be you get, which is Q, implies that you are. So you see what you could say is you get a speeding ticket. So if you get a speeding ticket, then that implies you've been over speeding. And so this would be P. Okay. Construct a truth table for each of these compound propositions. I feel like you guys have we already been through this up earlier, so I'm gonna skip this part. I don't want to bore you with it. This one, again, we did it earlier. We did an example. This is the exact same way. You want to put this number, put this under it, or the other way around. Put this number and put this under it. It's the same thing. And that ends lecture 1. Hope you guys found it useful. I'm going to try to cover all the lectures for discrete. No promises though. So if I don't come yell at me. place on Fragile. Goodbye.